Hi everyone, this is the third video in a 5-part series on how to solve the Schrödinger equation for the quantum harmonic oscillator. So I'm just going to start with a very brief recap of where we are so far, what we've done in the first two videos. So we started with the Schrödinger equation for a harmonic potential. We made a change of variables, so our position variable x was rescaled to be this y variable over here. Now energy E was rescaled to become epsilon. When we made those substitutions into the Schrödinger equation, we found that basically all of the constants disappeared, and we're left with this simplified dimensionless form of the Schrödinger equation over there. So then what we did last time was to look at the limiting form of that differential equation when y is very large, get an approximate solution, and use that to make an educated guess that the functional form of the full solution for our wave function phi may be some polynomial function of y times e to the minus half y squared. And when we made that substitution into our differential equation, we found that the polynomial, the supposed polynomial function of y, has to satisfy this new second order differential equation here. So in this video, we're going to consider one way in which we can solve that differential equation for p, and we're going to consider some of the implications of that solution, and particularly we're going to see how it leads to the quantization of energy, which is our first very interesting result about the quantum harmonic oscillator. So we're expecting or hoping that p as a function of y is going to be a polynomial function, but we don't know the degree of the polynomial. So what we're going to start off by doing is write p as a power series, which has an infinite number of powers of y. So most general power series we can write is p is the sum from I equals 0 up to infinity of some coefficient indexed by I times the ith power of y. So we're going to substitute that trial power series solution into our second order differential equation and see what that implies about the coefficient ci. Now in order to do that, we have to differentiate a trial solution for p twice. So let's first differentiate once, and you say p dash meaning dp by dy. Well, we can just differentiate it term by term, so it's still a sum where I goes from 0 to infinity. This time, when we differentiate y to the power of I, we pull down a factor of I, so you get I ci, but now your power of y is y to the I minus 1, just by differentiating the ith term there. Then we're going to differentiate that a second time, so I'm going to say p double dash, the second derivative of p. Again, it is a sum over all values of I, so sum where I goes from 0 up to infinity of I times I minus 1, this time because you differentiate this y to the I minus 1. You've still got your ci coefficient in there, and you've got to decrease your power of y one more time, so now it is I minus 2. Now let's think about what's going to happen when we substitute those three series into our differential equation. Well, in particular, this middle term, this minus 2y dp by dy, when you take your series for dp by dy, right, and you multiply it by y, then the ith term in that series has a power of y, which is just y to the I, right? This is nice because the ith term of the series for p itself, right, this thing over here also has its ith term being proportional to y to the I. And so the second and third terms in our differential equation match up in terms of their powers of y. But what about this d2p by dy squared? Well, notice that the second derivative of y, its infinite series, the ith term is not proportional to y to the I, it's proportional to y to the I minus 2. So we're going to fix that little inconvenience by carefully relabeling our indices in our sum. So what I mean by that is we're going to take all the values of I and replace them with I plus 2. This is a completely acceptable thing to do as long as we're careful about the limits of the sum, right? Because all we're doing is relabeling the indices. What was previously called I is now called I plus 2. So we'll think about the limits of the sum in a moment, but your I term here is just going to be I plus 2, and your I minus 1 term is now going to be I plus 1 because it's turned into I plus 2 minus 1. So we've got now I plus 1 times I plus 2. Your coefficient is now ci plus 2. And this is the whole reason for doing it, is that the power of y is no longer I minus 2, but it's I plus 2 minus 2, which is just I. So now we've made the powers match up with the other terms from the differential equation. Now what about the limits of our sum? Well, the upper limit is still going to be infinity, because taking infinity and shifting its value by 2 doesn't change it because it's already infinite. So we can still put infinity there. Now, notice that the first term, previously the first term in our sum had I being equal to 0. If we're relabeling I as I plus 2, that would be like saying I plus 2 is equal to 0, and therefore we should start our sum from I being equal to minus 2 now. But then if you think about the first couple of terms, if you were to expand out that infinite sum, well, when I is minus 2, this I plus 2 bit is 0, and so the first term is guaranteed to be 0. When I is minus 1, that's the next term, then the I plus 1 is 0, and so that term is also 0. So the first possible non-zero term in your sum still has I being equal to 0, right? The first two terms are guaranteed to be 0. So we can actually change that first I term to just I being 0, right? So it kind of looks as if we haven't really done anything there, but there were two steps that we had to go through to carefully make sure that we'd done our indices correctly. So now all of our infinite sums for p and p dash and p double dash, the ith term is proportional to y to the I, and so we can substitute those into a differential equation. All of them are going to be summed over all values of I from 0 to infinity. So I can write the sum from 0 to infinity of a whole bunch of stuff there. Now your d2p by dy squared term will contribute this this I plus 1, I plus 2, c I plus 2. Now notice that all the terms are proportional to y to the I, so I'm going to write that y to the I not over here, but I'm going to factor it out of these big square brackets that I'm drawing. What about the minus 2y dp by dy? Well, we're going to have a minus 2. Our dp by dy was this sum over here, so we're just going to get minus 2 times I times ci from that, right? So minus 2 times I times ci, and this multiplication by y turns the y to the I minus 1 into y to the I. So that's all fine. What about the final term, epsilon minus 1 times p? Well, you just get a plus epsilon minus 1 times ci from that, right? So I'm going to write plus epsilon minus 1 times ci. All of that multiplied by y to the power of I and then summed over all values of I, that is supposed to be equal to 0. Now note that this relation that we've just derived, that is supposed to be true for all values of y. Okay. Now, if we want this to be true for all values of y, considering the fact that different powers of y are linearly independent functions from each other, right? For what I mean by that is if you have, let's say, some constant times y squared and you have some other constant times y cubed, for example, no matter how much y cubed you subtract from y squared, you can never make that be equal to 0 for all values of y, unless the coefficients themselves are 0, right? So if we want this infinite sum to be equal to 0 for all values of y, we need to set the square bracketed term equal to 0, right? So all of that stuff is 0, and that gives us a recurrence relation for ci plus 2 in terms of ci. So if we just quickly rearrange that and make ci plus 2 the subject, you get ci plus 2 equals, well, you're going to have a 2I times ci term, right, from that middle term when you take it over to the other side, and you're going to have a plus 1 minus epsilon, again from taking this epsilon minus 1 over to the other side, all of that times ci, and your denominator is just going to be I plus 1, I plus 2 from doing that division at the final step. So we're dividing that by I plus 1, I plus 2. So there is your recurrence relation for the I plus 2th coefficient in terms of the ith coefficient. And from that recurrence relation, we can get two distinct classes of solutions. So what I mean by that is, well, firstly, imagine that we know C0. So let's say C0 has been specified. If you know C0, then you can work out C2, and from that you can work out C4, and so on. You can work out all of the even, the coefficients of even powers of y, but that doesn't tell you anything about the coefficients of odd powers of y, right? So, on the other hand, if you knew C1 instead, if that had been specified, then you would know C3 from that, and then you would know C5 from that, and so on, and you would get all of the odd powers of y. And so if you were to only have the C0, C2, C4, and so on coefficients, then your polynomial would be an even function of y, and if you were to only have the odd powers, then your polynomial would be an odd function. Now, at this stage, we could still have a linear combination of that even part and the odd part as our overall solution. But I'll have a little bit more to say about that later on in the video. So we've now got a series solution to our differential equation for p, right? So in principle, we know p, but we haven't imposed all of the physical restrictions that we have to impose on our wave function. In particular, it should be finite, right, at all values of y, or all values of x, and therefore all values of y. Otherwise, you would have an infinite probability of finding your particle at some particular position, especially as y goes to infinity. You want your wave function to stay finite because you definitely don't want to have an infinite probability of finding a particle infinitely far away from the minimum of your potential. So what we're going to do to address that potential issue is look at what happens to this recurrence relation when I gets very large, because when y is large, then the dominant powers in your polynomial are going to be the highest powers of y. So if we look at the large I behavior of our recurrence relation, then we'll get an idea of how our polynomial is behaving, or our series solution at the moment is behaving for large values of y. So I'm just going to write, as I goes to infinity, what happens? Well, your ci plus 2 is going to be roughly equal to the numerator of that recurrence relation is going to be approximately 2i. When I is really big, you can just ignore the 1 minus epsilon, so that's going to be roughly 2i over, and then the denominator, you can ignore the plus 1 and the plus 2 when I are really large, and so you get divided by I squared, and then that whole thing is multiplied by ci, and so this is roughly 2 divided by I times ci. So this tells us how the coefficients of our series solution, different powers of y, behave for the largest powers of y. But remember, our full wave function was not just that polynomial, but it was p of y times e to the minus a half y squared. So we should also really investigate how that exponential term is decaying. And more precisely, what I mean is we have to look at the series expansion of e to the minus a half y squared and consider how its coefficients are changing for large values of y. Now, for reasons that are going to become clear a little bit later, instead of just considering e to the minus a half y squared, I'm going to consider e to the ky squared, just to keep this general. And so the specific case that we care about for our solution is k being minus a half, but it's going to be useful to do this more generally. And we're going to think about the series expansion for this. Now, this is a standard result, which I'm not going to derive, like an exponential function. Its series expansion is just sum from I going from 0 to infinity of 1 over I factorial times the exponent to the power of I. Here our exponent is ky squared, and that should be to the power of I. And if I just expand those brackets, we can say that this is the sum where I goes from 0 up to infinity of k to the power of I divided by I factorial times y to the power of 2i. Now, what does that imply about the recurrence relation that we would get between the coefficients of that series expansion? Well, we've got to be a little bit careful with this because of the fact that we don't have y to the I, but we've got y to the 2i. So your ith coefficient, let's call it ci. I'm going to call it ci dash just to emphasize that it's not the same coefficient that we had in our polynomial, but the coefficient of I in the series expansion of e to the ky squared. We're calling that ci dash. Now, from looking at the term that we're summing up there, right, you're going to have a k to some power divided by some kind of factorial, but your power is not just going to be I, it's actually going to be I divided by 2, right? Because this I here, to which the k is raised, is half of the 2i to which the y is raised. So if you want the coefficient of y to the I in that series expansion, then k will be raised to half of that power. So k to the power of I over 2. Similarly, your factorial at the bottom has to be I over 2 factorial for the ith power of y. So if you consider the ratio of the I plus 2th component over the ith component, in other words, ci plus 2 dash over ci dash, well, you're going to get you're going to get a prefactor in terms of k, where you're going to get k to the power of I plus 2 divided by 2 divided by k to the power of I divided by 2, right? So that's coming from the numerator of my ci dash there, and on the top we just replace the I with I plus 2. Then you're going to get a ratio of factorials, which is flipped upside down because the factorial is on the denominator of your coefficient. So you're going to get I over 2 factorial on the top, and you're going to get I plus 2 divided by 2 factorial on the bottom. Now notice that I plus 2 over 2 is the same as I over 2 plus 1, right? So that combination appears as the exponent of k, and also down here in this factorial, right? So that is just I over 2 plus 1. So this actually simplifies quite nicely, because k to the power of I over 2 plus 1 divided by k to the power of I over 2 is just k to the power of 1, right? The I over 2 is cancelled. So that prefactor is just k. What about the factorial term? Well, you're doing the factorial of some number I over 2, and you're dividing that by the factorial of the number which is 1 greater than that, which is I over 2 plus 1. Now, if you imagine, remember the definition of a factorial, where you just take all the numbers from your starting point down to 1 and just multiply all those numbers together. If you expand those factorials as multiplications, then most of the terms are going to cancel because they appear both in the top and bottom. The only term which appears in the bottom which doesn't appear in the top is I over 2 plus 1. The rest of them, all of the smaller numbers, will appear in I over 2 factorial as well. And so you can cancel most of those numbers down, and that second fraction just becomes 1 over I over 2 plus 1. And then as I goes towards infinity, then this tends towards k times 1 over I over 2, which is the same as 2k over I. So the behavior of the series expansion of e to the ky squared when I gets very large, which is relevant when y is very large because the largest powers of y will dominate there, you get this recurrence relation where the ratio of ci plus 2 to ci is 2k divided by I. So what's the point of going through all this? Well, we can make two interesting conclusions. Firstly, if you consider the case where k is minus a half, right, that would just give you minus 1 divided by I. So your e to the minus half y squared is decaying in such a way that the coefficient ratio is approximately minus 1 over I. Okay. Your polynomial, or your power series, is growing in such a way that the coefficient ratio is 2 over I. So you've got a growing function multiplied by a decaying function. In order for that to stay finite, the decaying function must be decaying more quickly than the growing function is growing, which we can see from those recurrence relations is not actually happening, right? Because the dependence on I of both of those is just a 1 over I type dependence. So that already suggests that there is a possibility that our wave function is going to become infinite when y is very large. You can also look at this another way. This is why I did the expansion of e to the ky squared and kept it general, because this 2 over I times ci is basically the same as this 2k over I down here when k is 1, right? So that means that your series expansion is actually behaving like e to the power of y squared when y is very large. Now, e to the power of y squared is growing more quickly than e to the minus a half y squared is decaying. Okay, so all of this suggests that the conclusion of all of this, which I'm going to write down here, this is a very important point, is that p of y, that series expansion, must terminate. It must terminate. In other words, it shouldn't have an infinite number of terms, right? It must terminate at some I. Otherwise, your series expansion is going to behave like e to the y squared at large values of y and make your wave function infinite. The only way we can avoid that is if you don't actually have an infinite number of terms in your series expansion. So here's where we get to do some interesting physical interpretation of all of this maths. Now, if you look at the numerator of your series, your recurrence relation, the fact that p of y has to terminate at some particular value of I means that your epsilon value has to be equal to 2n plus 1 for some natural number n, right? The reason this works is that when you go through your series expansion, there'll come some point when I is equal to n. When that happens, your next coefficient is going to be 0 because the numerator of the fraction becomes 0. And therefore, all of the remaining coefficients in your series expansion are also going to be 0. And so your series expansion doesn't grow too quickly and your wave function actually remains finite. Now remember that the meaning of epsilon was it was this rescaled energy variable, right? So if we now substitute back that epsilon is 2e over h bar omega, where omega was the parameter from our quadratic potential, you can find that your energy, E, energy variable, has to be n plus a half times h bar omega. Now, remembering that n can only be a natural number, the implication of that relation for E in terms of h bar omega is that there are only certain allowed values of energy E, right? If the energy is not some integer plus a half times h bar omega, then your wave function would just become infinite. And so that's not a physically allowed solution. So this is called the quantization of energy. We've just shown that the requirement for the wave function to remain finite at large values of y implies that the energy can only take certain values. In particular, the smallest possible value that the energy can take is when n is 0. So the smallest possible value of the energy for a particle in a quadratic potential is a half times h bar omega. That's called the 0-point energy. That's the lowest energy that your particle can have. And then the energy levels step up in units of h bar omega, and they just keep going higher and higher. We can also slightly rewrite our differential equation for P, right, that one in the middle there, because now we know that epsilon is 2n plus 1. We can substitute 2n plus 1 in place of epsilon. And so we arrive at the slightly revised differential equation P double dash minus 2y P dash plus 2n times P is 0, where n is a natural number. Now we can also learn something about the symmetry of the wave functions from this quantization of energy. So we're going to consider separately the cases where n is even and where n is odd, right? So let's first say that n is even. Now, if n is even, that means that your even solution, remember we said you have these two sort of independent solutions, the one that has all the even powers of y and then the one that has all the odd powers of y. If n is even, then the even solution is guaranteed to terminate at some particular value of I when I is equal to n. But the flip side of this is that your odd solution, which has only odd powers of y, is not going to terminate because n is even. And so when you're going through all the odd values of I, then it's never going to hit n, and those odd powers are going to keep going. So that implies that C1 and C3 and C5 and so on all have to be 0. Otherwise, your odd part of your solution would go to infinity when y goes to infinity. So if n is even, that means that P itself is an even function, and by extension phi itself is an even function, right? Because phi is P times this e to the minus a half y squared, and if both of those are even functions, then phi is an even function. So for even values of n, your wave function is an even function. You can probably guess what's coming next, but if n is odd, we can make exactly the same argument, but this time the even coefficients are forced, in fact even C0, the even coefficients are forced to be 0. Otherwise, your even solution would become infinitely large. And so your P function and your phi function would have to be odd functions. And so as you go up this sort of ladder of energy levels, starting from half h bar omega and going up in units of h bar omega, your wave functions alternate between being even and then odd, and then even and then odd, and so on. We can say that in a slightly fancier sounding way as the wave functions have definite parity, meaning they're either even or odd, and they sort of alternate between the two. So in the next video, we are going to be focusing on this P double dash minus 2y P dash plus 2np equals 0 equation. I'm going to introduce something called Rodriguez formula, which is a very neat way of writing the solutions to that equation in a way that doesn't involve power series. I'm going to prove Rodriguez formula, and then we'll work towards finally writing the overall solution to the quantum harmonic oscillator. So thanks for watching, and see you again next time.